Okay, let's have a look at one more of these. So I got this disc sander, and we want to figure out what the safety factor is for the disc sander with respect to eventual failure of the shaft. So what we're going for here, we know that it has a basically a stall torque of the motor. So basically, there's a certain maximum amount of torque that we can apply that it can apply. So that limits that's kind of our maximum loading condition, and that occurs at 12 when the torque applied is 12 Newton meters. So if we have this force here, it's being applied over a 100 millimeter span here. That would be the amount of torque generated. So 12 Newton meters is equal to Ft times, it's just 0.1 meters. And for our Ft there, that's going to be equal to 120 newtons. So that's kind of the friction force that gets developed there as well. So basically, we know that we were given the coefficient of friction of 0.6. So we know that the ratio between the coefficient of friction and the normal force is a function of that. So 0.6 is equal to Ft divided by Fn here. So we can just solve for Fn, the normal force that's being applied. That's going to be equal to Ft divided by 1.6. So 120 newtons divided by 0.6, which, if I'm not mistaken, should be 200. Yep, 200 newtons. So we've got this Fn here, that's 200 newtons. So we've got enough to kind of figure out what the loads are going on here. So basically, we are going to have torque, axial, and a bending moment. Unlike most of the loading situations, we're not having a bending moment that's caused by a downward force. We're having a bending moment that is caused by a horizontal force that's offset vertically instead. But you know, it ends up being the same thing. So essentially, they're asking us for what happens kind of at this shoulder here, where we've got the the main input shaft, and then it's kind of machined down. So this is like the shaft coming out of the bearing here. The 18 millimeters is the bearing bore, and the 16 is kind of the main size of that shaft there. So we are worried about the fatigue that is going to be happening based on cracks that are growing like that. So what's going on here is that, well, okay, so we'll start by going ahead and having a look at our KTs, basically. So, where is that? Stress concentration factor, KT. So that's found in juveniles on figure 4.35. And we're worried about, all the bending, the axial, and the torsion. So I'm just gonna go and copy that into OneNote here. Make it a bit bigger so you can see easier. Okay. So our D over D ratio, our big D over little d ratio is 18 over 16. That's 1.125. And then the radius of the notch there, that's 5 millimeters. So our R over little d ratio is 5 over 16. R over D is equal to 5 over 16, so 0.3125. So a relatively high R over D ratio. So basically, we're going to have to kind of, what am I trying to say? We're going to have to kind of, basically we're hitting the end of the charts here. So basically, I'm just going to end up using the 0.3 value instead. So for the bending moment, first off, let's figure out what the bending moment is. So the bending moment is caused. Bending moment is caused. Come on, let me select the gem eraser. Or not. So the bending moment is caused by that 200 Newton force that is going horizontally, and the moment arm over which that's acting, that is, I think here. That's 100 millimeters. So the M is going to be equal to 200 newtons times 100 millimeters. So 20,000 Newton millimeters. It's going to be the bending moment caused by this force here. We've also got this force here, and that one is also going to be causing a bit of a bending moment as well. So basically, that's acting out this way. So that the 200 Newton force is going to be causing a bending moment about this axis. I guess I should define our axes. Let's see. Let's make this one. Let's make this the x-axis. This is the y-axis. This is the z-axis. So that the 200 Newton kind of normal force that's causing bending about the y-axis. The 120 Newton kind of friction force, the force that's causing the torque, that also causes a bending moment. So that is going to cause a bending moment, but again, it's acting kind of in this direction, so that's going to be causing a bending moment that is about the it's acting in the z direction and it's displaced in the x direction, so it's causing a bending moment in the about the y-axis. So our bending moment about the z-axis is the 20,000 Newton millimeters. Bending moment about the x-axis, sorry, about the y-axis, that's the 120 newtons times the 50 millimeters. So that's 6,000 Newton millimeters. So we get those two. Now basically what we're going to want to do is basically just combine them. So they're acting about different axes that are perpendicular to one another. So we can figure out what kind of the resultant of that is just by using Pythagoras' theorem. So square root of 20,000 squared plus 6,000 squared is 20,880 Newton millimeters. So we got that bending moment, and let's see here. So if we want to zoom in a little bit here, we're looking for the d over d of 1.125. So looking in here, that places us just above this line. So I would say that would be, that looks to me to be probably about 1.24. I think would be my best guess right there. This is a 1.3 line. It's not quite halfway there, halfway between 1.2 and 1.3. So yeah, 1.24 sounds reasonable there. So KT is equal to 1.24. Let's go ahead and figure out what our Q values are going to be too. While we're at it, since that gets used for all three of them. So our notch sensitivity factors, stress there we go. So I want to figure out what our notch sensitivity factors are. So our notch sensitivity factor depends upon the notch radius, which in this instance it was 5 millimeters. So we're going to end up with a value, you know, kind of around here. Along that line, but that's obviously, yeah. Again, we're off the end of the charts, so I'm just going to use the value at the end, and then we need to know what our our Brinell's hardness number is, or ultimate strength can also be used to estimate that. So again, we were given, this one has an SU of 900 MPa, which of course, unfortunately, this chart is in KSI, so let's just go figure out what that is. 900 MPa in KSI, I'm just typing that into Google on another screen, so 130 KSI. So a bit above the this 140 line here for the bending and the axial loads. So again, I'm going to zoom in on that. So this here would be for the 140. This here would be for the 200. Oh, sorry, a bit below that. We're going for 130, not 140. So yeah. All right, this line, yeah, this line here is the 100. So we're looking at probably a third of the way down. So right about there, which, let's see here, let's put that, so that division here, this is 1 point, this is 0.8 here, this is 0.9 here. Let's say 0.88. Yeah, 0.88 sounds reasonable. Maybe 0.858. Well, yeah, let's go for 0.89. I think that's a reasonable one. So I'm just gonna put that down here. Q for bending an axial, that's equal to 0.89. And then we got to do a similar thing using the values for the torsion. Using the values for the torsion. So there we are a bit above that first line. So oh yeah, I can't. Here, just let me give it a second here. Why isn't it letting me erase this? There we go. So the top line there is the 180. The bottom, the second top line is 120. So we're looking at just just above that. Let's say 0.92. That sounds like a reasonably unconservative assessment. So Q tor is equal to 0.92. All right, so if our KT for the bending is equal to 1.24, then our KF is equal to 1 plus Q times 0.24. So our Q is 0.89 times 0.24. 1 plus 0.89 times 0.24. So KF there is going to be equal to 1.21. And while we're at it, let's go ahead and figure out what our bending stress there is. So we've got our sigma b, that's going to be equal to that times this. So 1.21 times 32 times the m that we calculated here based upon kind of the maximum orientation. All divided by pi d to the third. What do we got for d? 16. Pi times 16 to the third. 16 millimeters. Okay, so 1.21 times 32 times 20,880 Newton millimeters divided by pi times 16 to the third. So that will be equal to 62.8 MPa. Our units here cancel out to newtons per millimeter squared, so that's MPa. So I'm just going to move that. And move that down here to be a bit less cluttered. So we're also going to have some axial force that's going to be generated. Axial stress that's going to be generated due to the axial force. So that's just due to the Fn. Come on, OneNote, let me change that M. Okay, there we go. All right, so again, we're going to be kind of looking at where it comes off the graph here, and we are looking at a d over d ratio of 1.12. So I don't know, let's say around there. So that'll be probably let's go with 1.28. KT is equal to 1.28, which gives us a KF is equal to 1 plus 0.28 times the Q value, which is 0.89. 1 plus 0.28 times 0.89. There we go. That's KF of 1.25. So the axial stress, that is going to be equal to 1.25 times 4 times the load, so that's the 200 newtons. That is a terrible looking N, divided by pi times 16 millimeters squared. 1.25 times 4 times 200 divided by pi divided by 16 squared. So not too much. That gives us 1.24 megapascals. I'm not 1.2 megapascals. I'm not going to too significant. I'm not going down to the. Not going down that low. 1.2 megapascals for our axial. So again, I'll stick that down here. And then we got our torsion. So the torque that's generated again is the 12 Newton meters. Our KF here, or sorry, KT here. Zooming in, let's say 0.1. Yeah, it's a really tight squeeze there. 1.1. Let's just say 1.12. I think that's reasonable. So KT is equal to 1.12. KF therefore is equal to 1 plus 0.12 times the Q value, 0.92. 1 plus 0.12 times 0.92 gives us a KF of equal to 1.11. So as for our nominal, that times our nominal. Let's say our torque, our shear stress due to the torque is equal to 1.11 times 16 times the torque. So 12 Newton meters times 1,000 millimeters per meter. Divided by pi times 16 millimeters to the third. 1.11 times 16 times 12,000 divided by pi times 16 to the third. Again, that'll give us megapascals. So that'll be 16.6 MPa. Okay, so there we got the loads that are occurring. Now, if we want to figure out what's going on here, we need to kind of convert those to, we need to figure out which are steady and which are reversing. So, typically speak, if we're assuming that, worst case scenario is we're kind of just pressing that there. Each rotation, what we're going to see is we're going to see the bending stress be completely reversed. We're going to see the axial stress stay constant as you're pressing there, and the torque's going to stay constant in our worst case scenario. So since the bending stress is the only one that has any kind of amplitude portion to it, the SA is equal to the 62.8 megapascals. I could go to the the equation that we use to calculate the equivalent amplitude. But everything else would be zero, so we just end up, it's the only non-zero term there, so we just end up squaring that and then taking the square root. So not so much useful. The axial and the torque, those are going to be constant, so those are going to be entirely mean. So what we can do is we can take those and we can go to our equivalent formula. Let me show you where I got that. Go to our equivalence formula and plug that into here. So again, we already determined that this one, for this one, that's 0, that's 0. So the bending is all we've got. This one, however, the mean has a few non-zero terms, so we need to go and plug those terms into there. So again, I already included the stress concentration factors in the calculation. So what we need to do, we just need to plug our 1.2 that goes into here, and it goes into there, and then the 16.6 goes right there, and it goes right there. So our SME, so the mean of our equivalent combined stress. And when I say equivalent, again, I'd like to remind people that we're basically taking all those loads combined and transforming them in a manner that they resemble just a pure bending test. You know, just kind of warping Morse circle into basically what we're doing is we're using Morse circle in order to kind of find a certain orientation that at that orientation resembles a bending test. So this is 0, this is 0. So we end up with the axial 1.2 MPa divided by 2 plus the square root of 1.2 MPa over 2 squared plus 16.6 MPa squared. So 1.2 divided by 2 squared plus 16.6 squared. Square root of that is 16.61 plus 1.2 divided by 2. So that gives us an SME of equal to 17.2 megapascals. And then we got an SA of 62.8 megapascals. So if we were to chart our Goodman graph, we'd have a yield line somewhere. And what sort of values do we have here? So our yield strength is going to be 750 MPa. Our SU is 900 MPa. Let's say about there. And let's see, so our SAE, well, so we got a load line that looks something like this, because our operating point, let's see here, our operating point is somewhere around there. Slope of that line is 3.65. So there's our operating point right there. So we still need to know what SN is. So again, we'll have to basically go back to juveniles again. And if we go to, no, I didn't want to do that. Didn't want to take screenshots. There we go. So we're trying to find the safety factor with regards to eventual failure. So we're basically doing an endurance limit. So we want to find its endurance limit, and again we want to find the bending endurance limit, because when we do the combined stresses, it's all it's all in reference to a bending stress. So our Sn is equal to the Sn prime. I'll make that a bit bigger so you can read a bit better. Sn prime times Cl times Cg times Cs times Ct, again assume Ct is 1 unless told otherwise, and times Cr. So our Sn prime for steel is typically going to be, unless you have actual test data, in which case you use your actual test data, your Sn prime is typically going to be half of our Su, which in this case would be 450 MPa. Our Cl, because we took these combined loads and transformed them into basically an equivalent bending stress, we use the Cl for bending, which is equal to 1. Our Cg, well, let's look at the chart for that. So the size of our component, the radius of our component is 16 millimeters. So if we're kind of in, we're in the 10 to 50 millimeter range here. So let's use a Cl of 90. Sorry, 0.9. CS. So what were we told about the surface? We were told that the surface is machined. And that means that we can go to our figure 8.13, and we're going to be using this line here. And we know that the tensile strength of the material was 130 KSI. Yeah, that's the ultimate strength. So we're looking at this intersection right here. So moving that on over. So let's see here. That to me looks like 0.73. Maybe 0.725. Let's go with 0.725. And how about a CR? So let's see here. Does not look to me like they specified any particular reliability. So for the purposes of, so let's for now just assume that we're talking a CR of 1. Yep. All right, so based upon that, we calculate what our Sn is. Let's see, 450 times 1 times 0.9 times 0.725 times another 1. Can't believe I actually punched the times 1 in the calculator the first time. So 293 MPa. All right, so that'll be probably right about here on this graph, which means that we have our SNSU line there. Based upon this, it's fairly obvious that our operating line here, it hits the SN-SU line before it hits the SY-SY line. So we don't really need to concern ourselves with doing the other failure criteria. So just basically 1 over the factor of safety is going to be equal to the SAE over SN plus SME over SU. All right, so SAE is 62.8 megapascals divided by 293 megapascals. And then we got the SME divided by SU. It's supposed to be U. It's more like an N, lowercase n. Anyways, so the 17.6 MPa divided by 750 MPa. Obviously, these ratios cancel out. So what's that? 62.8 divided by 293 plus 17.6 divided by 750. That gives us 0.237. Inverse of that gives us our safety factor. So that gives us a safety factor of equal to 4.2. And yeah, that is that.